Test, 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 test.
So everyone, welcome to the session C. And it's my pleasure to welcome Alex Nietner, who will be talking about classical verification learning.
Hello, everybody. Good morning. Thanks for the introduction and the opportunity to speak. I'll present this work that I did with this great team of collaborators. Matthias Caro is around the conference. You've probably seen him already. Then there's Marcel Hinsche, Ioannou, and Sweke. Yeah, let's dig directly into it and start with the motivation. So nowadays, we all know the thing. Everybody wants to have some AI assistant because we are all too lazy to code or write our emails by ourselves. And if you want to do all this by yourself, then there are several limitations. Like most of us don't have a lot of good data. Most of us just have a computer, not like a huge server room. And most of us have, I'm not so sure about in this room, but in general speaking, most of us have little expertise of coding these systems. And in contrast, like they're the well-known big companies, they have a lot of good data, they have loads of compute power, and they have hired all the experts from the fields. So rather than trying to do things by ourselves, the natural solution is take some money and buy the service from them and be happy. Then, I mean, all of us have had the situation, I guess, going to ChatGPT, enter some prompt and realizing it makes some pretty bad mistakes every once in a while, and sometimes more often than we wish to. So it raises the question, in how far can we verify whatever the learning algorithm supposedly has learned? And this question in the classical setting was raised in 21 by Goldwasser, Rothblum, Schäfer, and Yehudayov. And they wrote a paper termed Interactive Proofs for Verifying Machine Learning, where they asked, can verification of learning be cheaper than learning? And which is sort of precisely the question at hand, because, well, if it was of a comparable price, then we could just do the learning ourselves. So yeah, for meaningful notion of verifying that the service that we are accessing does the right thing, at least the cost of the verification should be cheaper than the cost of the learning. And in more detail, what they considered, or one particular setting they considered that is of interest to us here, is where the service oracle, which we call OP for the prover, was stronger in some sense than the user's oracle, we call OV for the verifier. And this can be thought of as good versus bad data quality, for example. And the aim was to find some learning problem or set of learning problems where the cost of learning with respect to the user's oracle is more expensive than the cost of learning with respect to the service oracle. However, the cost of verifying with respect to the user's oracle is lower than the cost of learning with respect to the user's oracle. Now we are at TQC, so we do quantum. Yeah, I mean, the same question will eventually arise in some unknown number of years when we have well-working quantum computers and those fancy quantum learning algorithms that people came up with and will come up with over the next years or decades are running on those quantum servers. Again, most likely, many of the users won't have all this computing power, all this expertise, all the data. So we need some means of verifying these things again. So in this work, we asked the same question in the quantum setting. Is there a learning problem or set of learning problems such that learning requires a quantum computer and quantum data, but verification is possible by a classical computer? And a quick teaser, the answer is yes. Exactly. Quick side note, there are related settings like verifying, then people somewhat familiar in the field will immediately think of verified quantum computing, blind quantum computing, etc., etc. those are related, but those are not the same. That's all I say for now, but I'm happy to answer more questions about this later or after the talk. Okay, maybe we should have downloaded the slide. I don't know what happens here. I guess the verification did not succeed. I mean, I can't even exit the full screen mode. I'll download them quickly. Just a question of minutes. Okay. So that was the motivation. Let's go through some preliminaries first, so that you know what the words are I'm talking about later. So to start, let's introduce agnostic PAC learning. Quick overview. If you are not familiar with PAC learning, could you raise the hand so I roughly know? Okay. Then let me introduce PAC learning. So PAC learning, PAC stands for probably approximately correct, and probably means that it's like the task is a random algorithm. There's a probability about success, and the approximate means we don't want to solve the task exactly, but only in an approximate sense, which means like it's a learning task. So we have some concept class which we call D here of instances, which some algorithm A is given access by some oracle O, and it gets access to some unknown instance P from D. And then the algorithm interacts with this oracle some number of times. And then after that, it's supposed to output a hypothesis H from some hypothesis class. And then the hypothesis is evaluated with an error respected an error measure, which depends on some benchmarking class B. So here is like, say, this light green is the set of all distributions. Then we have a concept class, which is some subset of distributions. We have a benchmarking class, which we in general consider to be a class of functions. I'll tell in a minute how to identify those with distributions. And then there's a hypothesis class, which is the class of outputs of the algorithm, which usually one thinks of those as functions as well, but could be a randomized function, then it's a distribution again. So yeah. And in general, like this delta n is the class, I use this notation here in the talk as the class of distributions over n+1 bits, where usually the first n bits are thought as one partition, and the last bit is sort of an output partition in some sense, which you will see in a minute. So what is this loss with respect to which we evaluate? So here we take the classification error, which means we have some distribution over some x and y, and then we want some hypothesis that has as small as possible a classification error here. Clearly, if my p really is a distribution, so there is not a unique y for every x, then there will always be some error, but there are cases where this, like if this y is unique depending on the x, then this p corresponds in a sense to a function, and then there can be a zero error. And the error, like here, this error of the benchmark class is just the minimum over all the distributions in the benchmark class and the error over that. That's the minimal error in the benchmark class. Some quick words. Okay, if you don't remember all of those, just so you roughly have an idea. If people speak about proper learning, they mean that the hypothesis and the benchmark class is the same, meaning this red and the orange is the same. Like the output is also what the stuff that with respect to which we are benchmarking the algorithm. It's realizable, then this then D and B is the same. So the benchmarking and the concept class is the same. If it's agnostic, those are not the same. That means that this will be non-zero. And this is the interesting thing and the stuff that we consider. And if it's fully agnostic, or that's our term for this thing here, we say fully agnostic if this D is literally the class of all distributions. And as I said before, like this, yeah, we can identify a distribution on n+1 bits with just its marginal distribution on the first n bits, and then the conditional expectation or the conditional distribution of bits that's morally speaking the same on the last bit, like conditioned on the first bits. And yeah, if this phi happens to be a Boolean function, then we even can identify this distribution with a Boolean function, which is what we mean here. Okay. Then a quick example. Probably also many here are familiar with parity learning. So just to recap some things. Yeah, one common learning problem is parity learning, agnostic parity learning, which means we are given some samples from some unknown distribution. And the task or the benchmarking class is the same as the hypothesis class, which is the class of our parity functions. And the task is to find some parity that minimizes the loss. And if you think about this in terms of the conditional expectation value, and if we if you think of this in terms of the conditional expectation value, and if we assume that P has uniform margin on the first n bits, then this just means that we want to find the largest Fourier weight of the conditional distribution. And a quick observation, the distribution corresponding to the parity functions in case of noise can be written as this here, which is then precisely the noisy random example oracle for learning parity with noise. And as such, this problem contains LPN, which is something we use in our results. Okay, that was agnostic learning. Yeah, the rigorous definition. So again, here is the graph how the protocol roughly works, and like yeah, usually we have a random example model oracle. Then there is, independent of what algorithm we use, there will always be some probability. So there is some requirement on the probability of success and the error. And so yeah, in agnostic Pak learning, we require that the algorithm with 1 minus delta probability solves the task where the task is to find some h, which has at most this error. This alpha, if you're not familiar with this alpha, it's just another variable that you can put in there to have more control on how strict or loose the task is. Like for large alpha, the task is looser than for tight alpha. Like for alpha 1, it's sort of the tightest. Exactly. And I think it's this because you're time. And now what is the setting for verifiable learning? Again, we have a nice flowchart. It's a little bit more involved now, but not much. Instead of just one algorithm, we now have an interactive prover-verifier pair. And like the prover and the verifier each have their own oracle. And yeah, but they have oracles with respect to the same unknown distribution. They interact with one another for some while, and then the verifier is asked to output either a reject, in case he doesn't trust the interaction, or he outputs a hypothesis, which then has to again has to obey some property given the benchmarking class. And there's a completeness condition, like in all interactive protocols, interactive proofs, that when P is the honest prover, then the verifier will, with probability 1 minus delta at least, accept the interaction and return some hypothesis such that the agnostic learning criterion is satisfied. In contrast, the soundness condition then is for any dishonest prover that can be computationally unbounded, with probability at least 1 minus delta, V either rejects or it returns a valid hypothesis. Okay. Then with that, let me tell you what we found out, or what our contribution was. So first of all, we wanted to do quantum learning in the agnostic Pak learning regime. And yeah, so we need some meaningful quantum oracle for this. And usually in quantum learning, people consider in quantum Pak learning, people consider the quantum Pak oracle, which is the one is given copies of this quantum state. So for a distribution, this is the quantum Pak oracle. For a function with respect to some distribution over the inputs, that is the quantum Pak oracle. And this oracle is great for functional agnostic, by which I mean that the concept class is a class of functions, not of general distributions. Yeah, if the concept class is a function class, then, and one is working over the uniform distribution, then this oracle is great. One can do Fourier sampling, etc., etc. But it's not clear how this is for the distributional case. It is not known that it's hard for the distributional case using this oracle, but it is not a straightforward way to reduce to the previous, like to the functional case. If you write down the Fourier thingy things of this oracle, then you will end up in a confusing mess. So we introduced a new oracle. I was motivated by some old work in the computer science, where we identify with, so first of all, we write our distribution again as a marginal distribution and the conditional distribution. And then we identify our distribution with a random function family, which is defined such that, yeah, this is the definition of the random function family, which you can think of as, like like this line essentially just means for every input, for every x, you randomly, according to this conditional distribution, sample the value of the function. So that gives you the random function family. And then the mixtures of superpositions oracle, as we call it, then is this quantum state. Yeah? So instead of just having a pure quantum state, we have a mixed quantum state, and it is so this quantum Pak oracle often is also called a superposition oracle, and we have a mixture of superpositions with respect to all the function families, functions in the random function family. And yeah, with this oracle, we then were able to show some nice things. So first of all, in the distributional agnostic quantum Pak learning setting, so we're not yet doing verification, we're just doing the learning. Yeah, exactly. There we found a number of theorems, just put them all in here already. So first of all, we could show that there's a quantum algorithm that can efficiently approximate samples from the Fourier spectrum of phi. So we could efficiently do approximate Fourier sampling, where the approximation depends on some details, but it is good for the things we want to do afterwards. It's not exact, that's crucial. I mean, it's not crucial, but it's sort of a crucial limitation. And with this approximate Fourier sampling, we can do one agnostic parity learning for any distribution, and we can also do two agnostic Fourier sparse learning from any distribution. And Then for the verification, unfortunately, we cannot verify this for all distributions, but there's a subset of all distributions on which we find that that the corresponding learning task is hard for classical learners. Yet we can efficiently solve it from an interactive protocol of this type as sketched before, where the quantum prover has access to a mixture of superposition oracle, and the prover has either statistical queries or random example access. And the same thing for two agnostic Fourier sparse learning. So this already gives us precisely the separation that we were looking for, a task of learning where classically the task is hard to learn, but in an interactive protocol with the quantum prover, we can verifiably solve the task. However, there are also limitations to our nice mixtures of superpositions oracle. So what I said before was that the distribution class was always had uniform marginal. And as soon as we drop the uniform marginal, as soon as we go to the distribution independent case, similar to other results in quantum learning, I note, we find the limitation that for the agnostic learning, the task of agnostic learning using mixtures of superpositions, the query complexity still is lower bounded by the VC dimension of our benchmarking class. This is sort of the same lower bound as in learning concept, learning settings. And for the verification, this is quite a nice bound we found, that in the distribution independent setting, the verification is bounded by the square root of the VC dimension. So there can be an improvement for the verification, but it will only be quadratic. This is very much similar to the work by, I think it was De Wolf and others, about the quadratic speed up in quantum learning. That for distribution independent case, that's the best you can hope for. Okay, well, how's the time doing? Okay, then I go directly to the discussion. So to overwhelm you, a large table of results that you can find in our paper. And let me just add some open questions that may be interesting for some of you to consider. So of course, this mixture superposition oracle, it's a cool thing. We can do cool stuff, but it's, to be honest, we don't know whether it's efficient. If it's just the uniform distribution, then one can efficiently prepare it because it's just the all plus state. But in general, we have no idea whether there's some efficient way of, given some efficient to sample from distribution, how to efficiently prepare this oracle. Then, as I said, there are no known results for the agnostic learning setting given the standard quantum Puck oracle. So it would be interesting to know, is there separation or are we just too stupid to obtain results? Then one can ask about verification in a broader sense. Here we asked about verify as classical. So what happens if we allow both sides to be quantum, but one side is resource constrained? And stay tuned, there's upcoming work in the next, I guess, 2 months with a bunch of more results. And obviously, as always, the question, is there some NISQ-friendly variant of verification? Because all I said here is probably only in 10 to 20 years, if at all. With this, thank you for your attention, and I'm looking forward to taking your questions.
So like for all the results here, they're all for just a uniform distribution?
So the lower bounds are for the distribution independent case. I mean, I must admit, I'm not sure whether one can get, it's possible, but I'm not sure whether one can get the same lower bounds if even restricting to the marginal being uniform. The upper bounds all had the restriction that the marginal is uniform, like the marginal on the first n bits. But I'm pretty sure one can relax this to like product distributions that are at least so and so uniform, like that have at least that are not completely biased. That's sort of similar, like more or less the same should hold as in the typical function Fourier sampling setting from quantum Puck queries.
Thank you.
I hope that wasn't too confusing.
So I'm wondering, so my question is more for the classical verification of classical learning, probably, but would it make sense to consider like maybe as like a zero knowledge kind of proof for learning? Is this something like a notion that would make sense?
It is a notion that makes sense, and this is what is going to be in our upcoming work. I mean, in particular in the quantum setting, this is something you can do if you have quantum interaction, like quantum communication. Then you can apply verification of quantum computing protocols to do precisely this, and they under the hood rely on some zero knowledge things. The classical side, I am. Yeah, like in the Goldwasser paper, you will find at least one result that does precisely that. Like under the hood, they don't explicitly call it like that, but they do that, yeah.
And I just so are there like cryptographic consequences? Like could one derive like, okay, if I can verify these kind of things, then this happens in cryptography or vice versa?
It's a question where I admittedly I don't have a concrete answer, but I can tell you what my rough understanding is. Like I think that the main issue in transferring from learning, like the results from learning to cryptography, is that in learning all we do is with respect to some oracle, and it is very dependent. And in cryptography, we want something that is of a computational nature usually. So this is sort of the gap that is to be bridged, and often in learning the efficiency or inefficiency has to do with the oracle being able to provide you data in a certain representation or not. And this is, I guess, the bottleneck.
Thanks.
And let me advertise tomorrow, Thursday, I also have a poster on another project about learning, but not the verification of learning. But feel free to also ask their questions about this one.
Yeah, that's exactly what I'm doing now. Yeah.
Yeah, thanks for the introduction. So one of the most basic principles in quantum mechanics is the so-called non-cloning theorem, where you know that given an unknown quantum state, we cannot create two copies of it. And this very simple principle actually has led to a lot of applications in quantum crypto, like seminal work of Wiesner in '83 that introduced quantum money. And we also have more advanced notions like copy protection and secure leasing, or so-called revocable crypto. And in this work, we introduce a new notion based on no cloning called local operations and classical communication, or LOCC, leakage resilience. Let me start by briefly talking about the previous no cloning based notions. For example, in copy protection, we encode a piece of software, a program, a function f into an unclonable quantum state. And we require that no computationally bounded adversary can create two working programs given only this one unclonable copy of the program. And like more, I guess, pictorially, we have this challenger that gives Alice this copy protected program, and Alice tries to split this into two quantum registers that are entangled. And bot one shard that receive this, but they're not allowed to communicate, but they're entangled, and they will try to keep using the program. A related and kind of mildly weaker notion is the so-called secure leasing or revocable crypto. In this case, we again encode a program into a unclonable quantum state. And we imagine, for example, like a company leasing out a piece of software for a limited amount of time to some user. And after their lease term ends, the user needs to return this program to the company. And after the successful verification of this returning of the program, Alice shouldn't be able to keep using this program, but the quantum state that it has kept with her, which could be possibly entangled with the state that's been returned to the challenger. Before moving on to our new notion of LOCC leakage resilience, let me talk briefly about leakage resilient crypto in a classical world. In standard crypto, usually the adversary attacks are cryptographic primitive through a very well-defined and strictly restricted channel. For example, in a signature scheme, the adversary will get signatures for some documents or messages, and it will try to forge a signature for a document that hasn't actually been signed by the authority. Or in public key encryption, the adversary will have the public encryption key, and it will try to learn the secret communication between two parties by looking at this ciphertext that has been sent back and forth between these two parties, and possibly some other related ciphertexts. And it also has a public encryption key. But in all of these models, the adversary actually has no information about the secret keys of the parties, which we assume that the honest parties keep like very secure, and the adversary learns nothing about it. This was the standard crypto. And in leakage resilient crypto, we ask the question, what if the adversary actually tries to learn at least a little information, like a partial information about the secret keys also? For example, in the signature setting, the adversary can get signatures for various documents, and it also learns some information about the signing key itself, and it tries to forge a signature for a new document. And this is practically very well motivated because researchers in the more practical side of things have shown that there are various ways of learning partial information about the secret key. For example, you could analyze the electromagnetic radiation emitted by the computers of honest parties when they're doing some computation that involve their secret key. You could do the same using some thermal imaging, or you could even just monitor their computer's power usage, like power profile, or you could even just observe the sounds emitted by their computers during computations involving their secret key. And all of these attacks have been shown to break very well-known cryptographic schemes that are actually secure in the restricted model where you learn nothing about the secret key. But as soon as you learn even some little information through side channels like this, the schemes are completely broken. So before defining leakage resilient crypto formally, let me quickly introduce public key encryption for people who are not familiar. In public key encryption, we have a public key that lets you encrypt messages, and we have a secret key that lets you decrypt ciphertexts. and we require some basic correctness where you can correctly decrypt ciphertexts. And our security notion says that given only the public key to the adversary and a ciphertext encrypting some known message M0 or M1, the adversary should not be able to distinguish these ciphertexts. An equivalent notion is this so-called game-based notion where the adversary gets the public key and it chooses some messages M0, M1, and it gets the encryption of a random one M sub B, and it tries to guess this output, this hidden bit B, and it shouldn't be able to do better than random guessing, which is a probability 1/2 correct, and so we require 1/2 plus negligible. Kind of a weaker notion of security for PKE is the so-called unpredictable security, where we require that the adversary, again, gets the public key and gets the ciphertext, this time of a random message. And it shouldn't be able to completely recover the encrypted message. So this is somewhat less meaningful than the previous notion where we require that you like almost learn no information at all about the message given the ciphertext. In this case, you could learn some parts of the message actually, and that doesn't necessarily violate the security. Right. So in the leakage resilience, we kind of have a similar game where the adversary again gets the public key, but this time it also gets this function, let's call it a leak of the secret key. Let's call it output L, and the adversary gets the ciphertext and also this leakage, and it again tries to guess this hidden bit, and it shouldn't be able to do better than random guessing. So here we actually didn't specify what this leakage function is, and we need to kind of impose some restriction here because we cannot just let it be any function. In this case, we could, and you could just output the secret key itself. Previous works have made this more concrete by various choices. For example, there's this whole line of research on bounded leakage where we require that the leakage function has a bounded output length. For example, it could be like 10% of the secret key length. Or we also have this noisy leakage notion where we require that the leakage that you learn doesn't drop the min entropy of the secret key by too much. And this is kind of modeling the case where there's some noise on the leakage that you obtain. Given the practical attacks, these are somewhat justifiable, but they're kind of still artificial, and you cannot know if they actually capture all possible leakage attacks. And the main reason we impose actually these restrictions are because, as I said, if you don't impose any restrictions on the leakage function, then you could just output the secret key itself, and there's no security. In this work, we introduced this new notion of LOCC leakage resilience, which is only possible using quantum computation. In this case, we consider the secret key as a quantum state, and the adversary, the leakage adversary, gets to measure this quantum state key arbitrarily and adaptively for any number of rounds, and there is no restrictions on the output length of the measurements either. And our justification for this model is that, as we just saw, like all known leakage attacks have been some kind of measurement on the computers of the honest parties that store the secret keys. But this single definition actually captures all of the known leakage attacks so far. Right. So more formally, again, we have this challenger that creates the quantum secret key, and the adversary gets to specify some measurement circuit, and it gets the leak measurement result, and it again adaptively specifies another measurement circuit and gets the measurement outcome, and so on for any number of rounds, for any polynomial number of rounds that's not very fixed. And at the end of this leakage phase, it again gets the encryption of some M sub B, so for some random B, tries to learn the hidden bit B, and we require that even given this huge amount of leakage, it shouldn't be able to do better than random guessing. So obviously, this is classically impossible because when just with one round, if there's no restriction on the output length of the measurement, you can just output the whole secret key. As I said, formally, we have this multiple rounds of leakage, and at the end of the leakage phase, you get the encryption of M sub B, and you're trying to guess this bit B. So the questions we ask in this work is, can we actually design cryptographic schemes that actually resist such a strong notion of leakage attacks? And another question that we're asking is, so as we talked at the beginning, there are other notions of no cloning based crypto like unclonable or copy protection crypto, or like revocable or secure leasing crypto? And is there a connection between this new notion of LOCC leakage resilience and these other no cloning based notions? And finally, can we even provide security guarantees even stronger than LOCC leakage resilience? In this work, we show that assuming distinguishability, obfuscation, and LWE, or those who are not familiar, these are, I guess, kind of strong but somewhat common cryptographic assumptions. Assuming these cryptographic assumptions, you can actually construct public key encryption schemes that resist LOCC leakage attacks. And assuming the existence of an object called quantum lightning, relative to a classical oracle, we can actually also construct a quantum money scheme where the adversary gets some banknotes, and on top of that, it also gets some kind of LOCC leakage on the secret key of the bank itself, and it still shouldn't be able to produce an extra banknote. And these are the feasibility results. In terms of connections to the previous notions, we actually show that in the most basic setting, this new notion of LOCC leakage resilience is actually implied by copy protection. Namely, in the unpredictable security setting, copy protection does imply non-adaptive, just like a single round non-adaptive leakage resilience, again, in the unpredictability setting. But we show that this implication actually doesn't go any further than this. Relatively a quantum oracle, we show that there exists a PKE scheme that does satisfy copy protection, but it doesn't satisfy even a single round of adaptive leakage resilience. And we also have some similar results on different cryptographic notions like signature schemes and pseudo-random function keys. And finally, we also introduce, again, another new notion, unique with quantum notion called intrusion detection, where we assume that the adversary is not trying to obtain some kind of side information on our secret key. It has actually completely broken into our computer, and in this case, it can just steal our secret key, actually. But we show that if we are using a quantum secret key, we can at least detect if something like this has happened. And this is, again, impossible classically, because classical information, you can just steal or copy someone's classical key without being detected at all. And we show that this new notion is equivalent to publicly verifiable secure leasing, another no cloning based notion we talked about at the beginning. And in particular, based on previous work, this gives us intrusion detection constructions for various crypto primitives, assuming against some cryptographic assumptions. So before moving on to like connections to previous notions, let me more formally define the previous no cloning based notions. So in copy protecting, as we said, there's some kind of functionality encoded into a quantum state that we're trying to clone as the adversary, and we shouldn't be able to do so. More formally, in the case of public key encryption, in the so-called CPA setting, we will have this adversary that gets this secret quantum key and tries to split this into two quantum entangled registers. And after the splitting, these adversaries, Bob and Charlie, are not communicating, because if they could communicate, they could just ask each other to decrypt things. And after the split, they get these random challenges, encryptions of random B, and they're trying to guess simultaneously the hidden bits, hidden challenge bits, B sub B and B sub C. So here we require that they cannot do so simultaneously with probability better than 1/2 plus negligible. So here the baseline security is actually 1/2, because what Alice can do is she can just give her key to Bob, who can decrypt correctly, and Charlie can just randomly guess its challenge. So the baseline is 1/2. We also have the unpredictability setting similar to classical PKE. Again, Alice splits her quantum key, and this time Bob and Charlie get encryptions of random long messages, and they're trying to guess the message in full. Again, this is kind of weaker than the CPA version because they could possibly learn some parts of the message. In terms of the relationship of our new notion of LOCC leakage resilience to previous notions, Naively, it might look like it should be implied by copy protection. After all, measurement outcome is classical, so the leakage information is classical, so which can be copied. What we can do is, in the copy protection experiment, we can just pretend or simulate the leakage adversary, and whatever leakage we obtain, we could just clone it since it is just classical. And this should probably break the copy protection, which means that copy protection should imply leakage resilience. So this does work in the very simple setting of unpredictable copy protection implies unpredictable, non-adaptive, like just a single round of leakage. Basically, we're doing the reduction I just described. Suppose you can break the leakage resilient experiment with some inverse polynomial probability. And in the copy protection experiment, you just simulate this leakage, get the classical leakage outcome, and you just copy it and give it to Bob and Charlie. And by some like Jensen's inequality argument, we can show that even though we have like two adversaries that are trying to win in this case, as opposed to just a single adversary in the LOCC case, this is just going to be like an inverse polynomial still. So this does break unpredictable copy protection, which gives us this implication. But this does work in the most simple setting. But what about CPA style security, where we're trying to guess, like we're trying to learn any information at all about the messages? As I said, in the unpredictability setting, like there's no guarantee that prevents us from learning parts of the message. In CPA style security, we know that you have no information at all about the message encrypted. And also, this was just like one round of non-adaptive leakage, where the measurement circuit itself is part of the adversary algorithm description. It doesn't depend on the public key at all. It could get public key as the input, but it's not specified by the adversary as a thing that depends on the public key. And we just have like one round of leakage. What about like more rounds of leakage? In the original definition, we defined it as having any polynomial rounds of adaptive measurements. So going beyond the very simple setting, we have actually two challenges. So the first challenge is that, as we just described in the leakage resilience setting, we actually have one adversary that tries to win the security game. Whereas in the copy protection setting, we have two adversaries that are simultaneously trying to learn the messages that are encrypted. And a related challenge is that the leakage resilience adversary actually accumulates some kind of internal quantum state throughout this leakage experiment. So it adaptively specifies some measurement circuits for multiple rounds, and it could also do some kind of quantum computation locally that depends on both the leakage measurement that it has specified and the leakage outcome that it has obtained. And we cannot simply copy this state to create like two adversaries for the copy protection experiment, because again, the adversary's internal state is also quantum. For example, in terms of challenge one, when we try to do the same simple reduction from copy protection to leakage resilience, suppose you can break the leakage resilience with some probably like 1/2 plus 1 poly. In the copy protection experiment, you can just simulate leakage and copy the leakage outcome. But in this case, we will have two adversaries. Again, they win with probably like kind of squared of the leakage resilience adversary winning on its own. In this case, it's going to be like 1/4 plus 1 poly. But this is like much lower than even the baseline attack of just giving the secret key to one of the adversaries and the other adversary randomly guessing this challenge. So this doesn't work at all. Second challenge is that, as I said, throughout the leakage experiment, the adversary maintains and accumulates some kind of quantum state on its side that depends on the leakage outcomes and the leakage choices that it has made. And to break copy protection in the reduction from the leakage resilience experiment, we will actually need to create two adversaries that win simultaneously. And we know that the leakage resilience adversary only wins if it uses this particular state that it has accumulated over the protocol. And we won't be able to clone this quantum state. But it affects even unpredictability security, which is like the weaker notion. As soon as we go up to like adaptive notion of even one round of leakage, and for more rounds like two or any polynomial round of numbers, we have no hope. So we actually show that this is not a weakness of our proof techniques, because we've been just talking about a particular way of reducing copy protection to leakage resilience. There could be other ways that we cannot see immediately. But this is actually not a weakness of our proof techniques, but there exists a quantum oracle relative to which there exists a PKE scheme that does satisfy copy protection, but it doesn't satisfy even a single round of adaptive leakage. So in general, leakage resilience is not weaker than copy protection. So before moving on to these impossibility results of implication, let me talk briefly about our feasibility results. So we do have a public key encryption scheme that satisfies leakage resilience, LOCC leakage resilience, based on indistinguishability obfuscation and the learning with errors assumption. So let me talk about our construction. So we will use the so-called coset states, which consists of, in superposition, all the elements of some coset that is of dimension lambda over 2, where we have this random subspace and we have this random shift to get a coset. And we also have this random inner product phase here for some random element S prime. And this coset state satisfies this nice property that when you apply QFD, you get the orthogonal coset, or coset for the orthogonal subspace. And more importantly, this coset states satisfy a very strong notion of security called monogamy of entanglement, where it's kind of similar to the copy protection experiments. The challenger prepares some coset state, and it gives to Alice. And Alice tries to split this coset state into 2 parts that are possibly entangled between Bob and Charlie. And Bob and Charlie even get to learn actually the subspace itself later on, like the classical description of the subspace. And they're trying to output some vector in both the primal subspace and the orthogonal subspace. And we require that they cannot do that with probability better than sub-exponentially small in the size of the subspace. We also have like a random challenge version of this. This was implicit in some previous work. We formalize it in our work. So in this case, the adversary prepares like multiple coset states. And again, Alice tries to split them into 2 adversaries. And these adversaries later on also learn the actual subspace descriptions classically. And they also get some kind of random challenge telling them to output a vector either in the actual subspace or the orthogonal subspace. And they're trying to output such vectors, and they shouldn't be, and we show that they're not able to do so with probability better than sub-exponentially small in the size of the coset state. So actually, coset states have been really useful in designing copy protection schemes, but they're not directly helpful in designing leakage resilience schemes, because there's like no notion of leakage or anything here. This is like very close to the copy protection experiment where you're trying to split some kind of quantum state. So we show a new property for coset states called LOCC leakage resilience for coset states. In this setting, again, the challenger prepares some coset states and gives them to Alice, and Bob specifies adaptively multiple rounds of measurements that will be applied to the coset states, and it applies, and it learns the leakage outcomes. And similar to the leakage resilience setting, after learning all these leakage outcomes, Bob also learns some kind of random challenge and actually subspace descriptions also. And it shouldn't be able to output vectors in the correct subspace, like the primal one or the orthogonal one, with probability better than sub-exponential, given all this leakage information on the coset states. So the proof idea for this new property for coset states is as follows. So as we said, one of the challenges in obtaining some kind of leakage resilience from copy protection type of security is that we will not be able to clone the leakage resilience adversary state and the reduction to the copy protection game. But luckily, in this case, we are in the information theoretic setting. So at least we can try to clone the leakage resilience adversary state in exponential time. But we still need to be careful because even though we have like unbound amount of time, we still have a single copy of the state that we're trying to leak on. For example, if we are trying to naively clone the adversary's state by just running it in parallel twice, they're very likely to specify different measurement circuits each round. And we just get to apply our leakage measurement once each round because we have like a single copy of the state that we're trying to leak on. But we can actually resolve this using the following idea. So we start with a very high number of copies of the adversary's initial advice that doesn't depend on like the public key or anything. Be able to determine this high number later on. And during each round, we actually run the separate copies of the adversary multiple times until we get like 2 copies, or to make this for multiple rounds, we will need to obtain like multiple copies. We just keep running the separate copies of the adversary until we get the same leakage measurement choice. And when we get the same leakage measurement choice, actually we can just apply it once and we can use the classical leakage outcome multiple times because it's classical, we can just copy it. What we do is, as I said, during each round, we use like a lot of copies from previous rounds, like inductively assume that we have enough copies from the previous rounds of leakage, and we repeatedly run our adversary. We're probably destroying most of the states that we got from the previous rounds, but at the end, we will try to obtain sufficiently number of copies of adversarial state for this next round of leakage. As I said, when we obtain the same choice of leakage circuit, we can actually just leak once and use it to create multiple copies of the adversary state that are conditioned on that same leakage choice for the next round. So there's still kind of a problem here because some leakage circuit choices might be like really hard to obtain. Even though you get to have exponential time, we still need to bound the total amount of time that we're using. But we show that this is actually not a problem in average because if some leakage circuit choice is really rare, then it's also not going to appear in an average for any single copy at all. So we actually show that given some like A copies of the adversarial state from the previous round and a fixed choice of leakage circuit, we can actually produce D extra copies of the state of the leakage adversary for the next round that are indeed conditioned on the same leakage circuit choice for any D with probability, I guess, this averaged over the choice of leakage circuit. I guess this is like a long way of saying that we can still bound the amount of time that we spend on this experiment, but at the end, we are able to actually produce 2 copies of the final internal state of the leakage adversary, which we can use in the copy protection experiment. And since we are in a like a negligible security regime here, and the squaring issue doesn't appear here, like you don't have an issue of 1/2 versus 1/4 here. Using this leakage resilience property for coset states, we can design a leakage resilient public key encryption in the natural way where we will have some kind of program as our ciphertext that actually verifies your coset state in some sense, in the sense of like the leakage resilience challenge. For example, the ciphertext will have a random challenge embedded inside it. And it will also have some programs verifying the vectors in the primal or the orthogonal subspace. And our ciphertext program gets as input the vectors that depend on this challenge that will also be given to the adversary. And upon successful verification of these vectors, which just basically emulate the challenger of the leakage resilience experiment for the coset states, if they are successfully verified, it just releases the hidden message. So I think it's kind of natural to see how this relates to the leakage resilience property for coset states. Okay. Okay, yeah. Yeah, so basically, this kind of naturally reduces to the leakage resilience property for coset states, at least in the black box Oracle model for the ciphertext programs. we need to do some more work for the cryptographic version where we assume distinguishability obfuscation instead of a black box obfuscation. And I guess how much time? Oh, okay. I guess we don't have. Okay. Yeah, as I said, one of our other results is that copy protection doesn't imply even one round of adaptive leakage. And to show that, you rely on so-called quantum lightning states where anyone can create a unclonable state, but even if they get to create their own state, they're not actually able to create two copies of the same state. And we crucially rely on the leakage adversary creating such a state on its side. And in the reduction, we won't be able to copy the state to create a copy protection adversary. And this gives us a separation between copy protection and one-round leakage results. That's it.
A very basic question about the general setup. So my impression is like the model is that so in the sense of how to the motivation in the sense of an application, like you said, there's for example a program, so the program provider has the program encoded in some state, it gives to the user, and then the user after some time gives back the state to make sure, and the provider can then check is the state still the same in order to make sure that the program was not cloned or copied or whatever.
Yeah, you're talking about the secure leasing setting.
Exactly, yeah. And like realistically speaking, I mean, pretty surely or at least I find it very, very, what I find interesting is that there could happen all sorts of things for disturbing the state without it being copying, like that, I don't know, there is some very strong sun ray hitting the lab of the user and perturbing the state in one way or another. And there is no way of distinguishing between the case there's something else that perturbed the state or it is perturbed because of copying. Is there any trend in the field of trying to figure out means of distinguishing these two cases?
So you're talking about an honest person, but their copy of the software somewhat gets damaged.
Exactly, yeah.
It's a good question. I don't think there's any on that. And it might be impossible to do, but I'm not sure.
Okay, thanks. maybe then. Something like.
Hello. You presenting? First one. It is not the fastest. I'm trying to. And I back. I hate them. That's Francesco. Hello. Okay.
I think should be there.
It's I downloaded already. It's
Yeah, exactly.
there you go.
And Mike is just this thing.
Yep, yeah, should be fine. You can put a slide.
How?
Nice.
I mean,
Yeah, you have to- you know how to use Mac?
Mac, yes.
Oh, I mean, as you have to scroll, right? You have to move to it's a different screen.
Ah. Okay. No? Okay, maybe.
Yeah. Because if you try to like manually
Sorry,
the
but
left, you're gonna show.
ah, okay, I see, I
See.
see. Yeah, yeah. Yes. Ah. Ah, okay, I take this.
Okay.
Try. Yes.
Right. Okay, it does not seem to change the slides, but I can do it via the computer. Yeah.
Hello. Okay. Hello, everybody. Let's go. Let's start the second and last session of the morning. So our first speaker is Francesco. He's going to be talking about quantum communication. So please take it away.
Thank you very much for the introduction. This talk is based on a joint work with Farzin Salek, that is also here at TQC conference, Vittorio Giovannetti, and Ludovico Lami. In this talk, I will talk about the combined effect of photon loss and dephasing. Photon loss and dephasing have been extensively studied in the literature, but only separately. The literature lacks a complete understanding of the combined effect of loss and dephasing in optical systems. In our work, we try to fill this gap, and we provide application to quantum communication and error correction. The outline of the talk is as follows. We give a brief introduction to continuous variable systems. Then I talk about the model to describe loss and dephasing. And then we talk about no-go results for communication and error correction. So continuous variable systems are basically quantum optical systems. Here, the role of one qubit is played by the so-called one mode. One mode is basically one qubit with d equal to infinite. Is an infinite dimensional qubit. The Hilbert space of one mode is the span of ket0, ket1, and so on. These are called the Fock states. Ket0 is the state with 0 photons, the vacuum state. Ket1 is the single photon states, and Ket-D is the state with d photons. So now let us talk about photon loss. You can imagine that you have an optical device, for example, an optical fiber, and you can input a single photon into the optical fiber. This photon has some probability lambda to be transmitted to the output, and some probability 1 minus lambda to be lost in the environment. And we call this probability that a single input photon reaches the output the transmissivity. Is a parameter in 0, 1, is a probability. And in order to model the process of loss in optical systems, people use the pure loss channel. It is a continuous variable channel defined as follows. It acts by mixing the input state rho in a beam splitter of transmissivity lambda with an environment state initialized in the vacuum. By tracing out the environment, you obtain the output of the pure loss channel. So a beam splitter is basically a semi-reflective mirror. And the pure loss channel is noiseless for transmissivity equal to 1, basically the identity channel, and it is completely noisy for transmissivity equal to 0. Just to forge our intuition, if you input the single photon state in the pure loss channel. Then the output is with probability lambda, the single photon state. And with probability 1 minus lambda, the photon is lost, so you have the vacuum. So this is the output of the pure loss channel when the input is the single photon state. Now let's talk about dephasing. Dephasing is a process that tries to transform coherent superposition into classical probability mixture. And in order to model the process of dephasing in optical systems, people use bosonic dephasing channel. It is parameterized by a parameter gamma called the phasing strength. Is a real parameter, positive. And the bosonic dephasing channel is defined as follows. It takes in input the density matrix written in Fock basis, and it outputs another density operator with the off-diagonal terms suppressed by this exponential factor. So you can see that it is noiseless for dephasing equal to 0, while it's a full dephasing for gamma equal to infinity. The state becomes diagonal in Fock basis when gamma is equal to infinity. And note that the Fock states are left unchanged by the action of the bosonic dephasing channel. Okay, this is the definition of bosonic dephasing channel. Okay, so these two channels, loss and dephasing, have been extensively studied. And in our work, we study the combined effect of loss and dephasing. In principle, if you have, for example, an optical fiber, loss and dephasing act simultaneously. You can imagine that you have an optical fiber at any position of the optical fiber, both loss and dephasing can act. So in principle, in order to model the loss, the combined effect of loss and dephasing, you have a weird composition of infinitesimal loss and infinitesimal dephasing channels. But fortunately, the pure loss channel and the dephasing channel commute. So in order to model the combined effect, their combined effect, you can we can model it by first the dephasing and then the pure loss channel, for example, on the other way around. This is the definition of loss dephasing channel. It is the composition between pure loss channel and dephasing channel. And in our work, we want to study this channel, the quantum communication capabilities of this. Let's recall some preliminary. Given a quantum channel, you can always associate a Stein spring representation. So you couple the input state of the channel with a Stein spring unitary with an environment state. And if you trace out the environment, you obtain the channel. Okay, instead of tracing out the environment, if you trace out the system, the output of the channel, you obtain another channel. This is called complementary channel. It is the channel that maps the input of the system to the output of the environment. This is the definition of complementary channel. And so the output of the complementary channel is the output of the environment. Now let's give the definition of antidegradability. A channel is said to be antidegradable if there exists another channel, A, such that the composition between A and the complementary channel is the channel. And in other words, if a channel is antidegradable, it means that the environment has more power than the system. This is because the environment can apply post-processing on the output state to recover the same state of the system. So this is why the environment has more power than the system. And this is also the intuition behind the no-go theorem for antidegradable channels. Basically, if a channel is antidegradable, okay, this is a known fact. If a channel is antidegradable, then it does not admit reliable protocols with vanishing error to perform quantum communication and error correction. This is formalized by saying that the quantum capacity of anti-degradable channels is 0. Okay, so anti-degradable channel, quantum communication, the error correction with vanishing error is impossible across anti-degradable channels. Just for our intuition, just give the sketch of the proof of this result, just a rough idea. It's because of non-cloning theorem, basically. Because if there exists a strategy to correct the noise, encoding and decoding procedure to correct the noise, then also the environment can apply first the mapping A and then the decoding to obtain the same state row. So basically you obtain a cloning machine. And so this is a reason that is a contradiction. So this is the reason why that the noise of anti-degradable channel cannot be corrected, a rough idea. So let's give an example. The pure loss channel is anti-degradable if and only if the transmissivity is in 0, 1 half. This is intuitive because the transmissivity is the probability that a photon is transmitted to the output, while 1 minus lambda is the probability that it is transmitted to the environment. So it's intuitive that this happens. And okay, the phasing channel instead is never anti-degradable for any finite value of gamma. And by combining these two facts, it easily follows this fact that the loss-dephasing channel is anti-degradable if the transmissivity is in 0, 1 half. This is a simple consequence of the first fact. And okay, what about the other region when the transmissivity is strictly larger than 1 half? Few years ago, it was conjectured that also the converse is true. Basically, that the loss-dephasing channel is anti-degradable if and only if the transmissivity is in 0, 1 half. It was conjectured that this is the only anti-degradability region of the loss-dephasing channel. And in our work, we show that this conjecture is false. And indeed, we prove that for any value of the transmissivity, also for those larger than 1 half, and all sufficiently large values of the dephasing strength gamma, the loss-dephasing channel is anti-degradable. This identifies a large parameter region of loss and dephasing where communication and error correction is impossible. And now I can show you this region where we put this no-go result for communication and error correction. So we put on the y-axis the transmissivity and on the x-axis the dephasing, parameterized as e to the minus gamma, just to have a parameter between 0 and 1, because gamma ranges from 0 to infinity. And the red region is the region where the channel is anti-degradable. So the no-go result for communication error correction holds. If you have an optical devices and the phasing and the loss falls into this red region, that you cannot have hope to design a protocol for communication. And in the crossed red green region, actually there exists protocol to perform quantum communication. So, okay, this is our main result. And okay, now I want just to give a sketch of the proof of this result, because it introduces some tools that can be useful. Okay, so we start by considering the choice state of the channel. Here there is written generalized because we are in continuous variable systems. Generalized choice state of the channel. And we use a known fact that a channel is anti-degradable if and only if its choice state is true extendable. True extendable means, okay, the choice state is true extendable by definition if there exists a tripartite state, A, B1, B2, such that if you trace away either B1 or B2, you obtain the choice state. So basically, look at this picture. you have the choice state is true extendable if there exists this tripartite state such that if you trace away B2, you obtain the choice state, or if you trace away B1, you obtain still the choice state. And okay, so this is the definition of true extension. And rho is said the true extension of the choice state. So the idea is to find an explicit construction of the true extension of the choice state of the loss-dephasing channel. Okay, this is hard in general. So in order to show this example, we use some tricks. By heuristic based on semi-definite programs, we find an explicit construction of a state such that its partial traces with respect to B1 and B2 have the same diagonal and the same zeros of the correct choice states, but not the same off-diagonal terms. So in order, okay, so we start from this state that is has some similarity to the correct choice state, and we want to apply some channels to it in order to make it a good true extension. And in order to do this, we employ the tool of Hadamard channels to adjust the off-diagonal terms. Okay, let's give the definition of Hadamard channel. So given a matrix M, possibly infinite dimensional, an Hadamard channel is a superoperator parameterized by this matrix, such that it acts as follows. It acts on basically Fock says as follows. It applies to at I bra j by multiplying the element ij of the matrix M. Okay, this is the definition of Hadamard channel. Okay, in general, this is not a quantum channel. It depends on the matrix M. But it turns out that HM is actually a quantum channel if and only if the matrix M satisfies the following condition. M is positive semi-definite. This is the completely positive condition of the quantum channel. And the diagonal of M is equal to 1. This is the trace preserving condition. So the Hadamard channel is a quantum channel if and only if M is positive as 1 on the diagonal. So the trick that we use is to apply to this state tau suitable Hadamard channels, such that if you trace away B1 and B2, you obtain the correct choice state. So we construct the matrix M such that as this operator has the correct partial traces. So it is defined in this way. Now the matrix M depends on the parameters lambda and gamma, on the transmissivity and the dephasing strength. But we need still to require the positive semi-definite condition. And this is a true extension if the matrix M is positive semi-definite, because if this holds, then HM, the Hadamard channel, is a quantum channel. So you are applying this quantum channel to this state. So this is a proper state. Otherwise, this is not guaranteed to be positive semi-definite. And okay, so the step 3 of our proof is to find the parameter region of lambda gamma where this matrix is positive semi-definite. And we do this by exploiting the so-called diagonally dominant criterion. Just to recall, the diagonally dominant criterion is a criterion to check if a matrix is positive semi-definite. And it says basically that if M is an Hermitian matrix, such that for any value on the diagonal, it majorizes the sum of the other elements on the second column. Like this 8 is larger than 2 plus 1. This has to happen for any element on the diagonal. Then it turns out that the matrix is positive semi-definite. Okay. We employ this criteria on our explicit construction of the matrix M to find the parameter region where the matrix M is positive semi-definite. And this parameter region is exactly the parameter region where this operator is actually a good true extension of the choice state. And so this parameter region is a parameter region where the channel is anti-degradable. And this is how we construct this red region where these no-go results on quantum communication error correction hold. Okay, so by summarizing, we have shown that quantum communication is impossible in a large parameter region of loss and dephasing. And now we ask what happens if Alice and Bob share a classical communication line. So imagine that Alice and Bob share a classical communication line, are assisted by two-way classical communication. Then we can show that basically if Alice and Bob are assisted by LOCC, local operation, and classical communication, then quantum communication becomes achievable for any value of the transmissivity and for any values of the dephasing strength. And even if you put energy constraints at the input of the channel. So while unassisted quantum communication is impossible in a large parameter region, quantum communication assisted by LOCC becomes always achievable. And this is formalized by saying that the two-way quantum capacity is strictly larger than 0. Actually, we found an explicit lower bound on the two-way quantum capacity. And okay, so in conclusion, in our work, we provided an analysis of the combined effect of loss and dephasing. And we proved no-go results for quantum communication and error correction in a large parameter region of loss and dephasing. And okay, this is a no-go result, but we also found a positive result that if you assist quantum communication with LOCC, then the communication becomes always possible. Okay. Thank you for that attention.
Thanks for a nice talk, Francesco. We have plenty of time for questions. Any questions? Okay, one there.
Hi, Francesco. Thanks for a very nice talk. So I just have a very simple question, which is not quite covered here. So does your result generalize straightforwardly to like multi-mode bosonic channels?
Okay, multi-mode. Okay, so you mean also multi-mode pure loss channels, right?
Yeah, so in quantum optical systems, oftentimes you consider many modes, even continuum, like sometimes. And
yeah, okay. Actually, I didn't think about that, but I mean, maybe it can be simple to generalize, but we can think about it later after the talk.
Okay,
but,
very good.
Yeah,
thank you.
I'm sure that we can try to answer this question.
Any other questions? I can get the microphone.
For the nice talk, I have a bit naive question. Your channel has two parameter lambda and gamma, right? So
yes.
What's the relevant, what's the typical parameter region that we expect in communication? For example, you have for all lambda, you have a very large gamma such that the channel is degradable. But is this, I mean, it's a channel is not losing, but has a very large dephasing. Is this like you have some concrete experiment or say concrete channel in mind? Or
you mean
what's a relevant parameter region?
Yeah, so sorry, can you repeat the question? I'm not sure if
in this parameter region, what do you think is which part is more relevant?
Okay, because yeah, you are saying there is this white region where it is not clear whether the channel is
yes,
okay.
yeah. What's
what we conjecture that is the true anti-degradability region is this green, the lowest green line, because okay, actually you can exploit semi-definite programs. You can embed your channel in a finite dimensional channel because the loss-dephasing channel maps the first default states to the first default states. So and this defines a qubit restriction of the loss-dephasing channel. And if the loss-dephasing channel is antidegradable, also the qubit restriction is antidegradable. And so if the qubit restriction is not antidegradable, you can understand that the loss-dephasing channel is not antidegradable. So by using these semi-definite programs, because the true extendability condition is a semi-definite program, so we can check numerically if the qubit restrictions are antidegradable or not. And but of course, just when D is small, because for numerical constraints. And this green line is derived by taking small values of D, like D equal 5 or D equal 6. And it seems that going through, for example, D equal 5 or D equal 6, this line do not change much. And so we think that, yeah, it should be something like that. It reaches a plateau in D at some point, but it is not. It just experiment. I mean, numerical experiments.
Further questions?
Oh, thank you very much. So you talked about some properties of quantum channels which hold, which are known in the finite dimensional spaces, but your scenario is about the infinite dimensional ones. So I wonder all the things hold naturally if infinite dimensional spaces.
Okay, what properties do you mean?
For example, can we define the quantum capacity in the natural way, and then can we say that every antidegradable channel in the infinite dimensional space can have the zero quantum capacity?
Yeah, it can be proved. This yeah, I mean this was not the proof. It was just a catch of the idea behind the proof. Yeah. But yeah, everything can be defined rigorously for continuous variable systems. For example, maybe you mean also the choice state? I don't know. For example, the choice state. Okay, the maximum entangled state does not exist in infinite dimension. But what I mean by generalized choice state is okay, it is defined like that. But this is the so-called two-mode squeeze vacuum state. With a finite squeezing parameter.
Thank you.
Yeah, my question is, can you describe more how the last part works? Like, is there a protocol that uses LOCC?
Yeah. Okay. Yes. So, okay, we have there are many few strategies that we come up with to make quantum communication via LOCC possible. And for example, what okay, maybe I can tell you this first. There are these multi-rail strategies. Okay, we encode. Okay, if Alice encode its quantum state, her quantum state in a subspace with a fixed number of photons. Okay, and then since okay, so for example, you encode 0 in ket 0 in ket 0 tensor ket 1, and ket 1 you encode it in ket 1 tensor ket 0. Okay, this is an encoding. It's called the multi-rail encoding, and Alice can send this encoded state in multiple uses of the channel, and Bob can check if the loss happened or not by making a total photon number measurement at the output. And if the output of the total photon number corresponds to the total photon number of the input, then and it will happen with some probability, then I mean, you have basically you obtain a state. Okay, this is with post-outcome measurement. It happens with some probability. You obtain a shared state between Alice and Bob that it is always basically distillable. You can always distill entanglement starting from these states after this multi-rail strategy. And if you transmit state, if you transmit entanglement states, I mean maximum entanglement states, then you can also use quantum teleportation protocol to sense qubit from Alice to Bob.
Thanks.
Let's thank Francesco again. There's this, right?
Yes, exactly. Perfect. Sorry. This thing maybe. But okay.
To move to, I don't know.
View. I think it's view.
They have to move to the screen.
It works, right?
That's working. You have to move.
Okay.
That's okay.
That's okay. Yeah. Robert, yeah.
Okay. Okay, the second speaker of this session is Robert. He's going to talk about robustness of fixed points. So please take it away.
Thank you. Thank you very much for the introduction and the organizers to let me speak here. So this is about some joint work with Bjarne Bergh and Ioannou, both at Ioannou both at Cambridge. And if you're interested in the work, we also have the preprint on the archive. So the work is about robustness of fixed point equations of states and channels. So let me start with the fixed point equation. This is how I write states. This is how I write CPTP maps or channels. And we have a fixed point equation if kind of the channel leaves the state invariant. And we want to study the robustness of it. So we introduce some error parameter epsilon. So we say we have an approximate fixed point equation if this fixed point equation holds true up to error epsilon in trace distance. And the overall scheme of this talk, or the motivating question is whether certain structural results which hold true for exact fixed point equations can be proven to hold also now up to small error for approximate fixed point equation. This is kind of like the scheme. And to approach this question a bit, I want to start with like a bit more concrete mathematical question. This is question one. So, okay, you could ask whether for such an approximate fixed point equation, there's always a new state which is close to an original one. So with closeness, I mean I have like an approximation function, possibly dependent on a dimension, which decays as this error parameter epsilon goes to 0. And I then demand that this new state is an exact fixed point of this new channel. Okay, this is some naive question. And okay, everyone who took a linear algebra course, so everyone in this room knows, nope, this is not true. This holds true for, or this is like impossible for general linear maps. I now have like a quantum state and channel example. So I can pick kind of rho to be the 0 state, n to be like almost the identity. I replace it with like epsilon probability with the 1 state. Because n is almost the identity, I obviously have like an approximate fixed point equation, but n has a unique fixed point state, which is the 1 state. This is far from rho, so I cannot fix the fixed point equation by just changing the state. Okay, maybe I can do the opposite. So this is some question 2. What happens if I only ask to find like a new channel, which is now close to the original one? Here I mean in diamond norm. I have a new approximation function g, which also should decay. And then I demand that the new channel has the original state rho as an exact fixed point. Okay, and this is maybe not immediately clear what should happen here, but now we can actually use positivity or the demand that the new map M should also be positive to find that this is also not possible. So this is the counter example. We can kind of like use it. It's like on a qubit or something higher dimensional. Rho is kind of almost a 2 state. So we mix it a bit with the 0 state. N is a unitary channel which replace or like switches 0 and 1, swaps them. So it's like the Pauli X on those states and doesn't do anything on the 2 state. And now, okay, we have an approximate fixed point equation because N is essentially doing nothing on the 2 state and rho is almost a 2 state. But now assume there exists a new channel M, which is close to N, such that we have an exact fixed point equation. And okay, rewriting this fixed point equation and putting them into like this expectation value with the one state. Okay, this just gives 0. Because rho doesn't have any support on one state, you get kind of like just this overlap. Then you can use positivity of m to get this inequality and just kind of like cut out the 2 part of rho. But now we use that m is close to n, and we know how n acts on 0. It just swamps to the 1 state. So kind of you get like this inequality, and because g decays to 0, for epsilon small enough, this thing is strictly bigger than 0. So now, okay, you read from left to right, 0 is strictly bigger than 0. So this is a contradiction, so this cannot hold true. Okay, so both questions have negative answers. Maybe if we now kind of do both at the same time, maybe we're more lucky. So it gets a bit more complicated. We want to change both state, both channel. They should be close to the original ones. And we want now an exact fixed point equation. Maybe this is now true, okay? We can actually make this even more complicated and be interested in like certain structures. All of the states and channels should satisfy. So these are parameterized by these sets S and C, which are introduced in red here. You can think of maybe you want them to be separable states or unital channels or something like that. And they kind of enter the problem in 2 ways, as a promise that the original state and channel are of that form. So you have kind of like some knowledge about them, but also as a demand that the new state and new channel are also of the same form. So kind of like on this level, it makes the problem easier, but on that problem, the introduction of these structures makes it harder. And if kind of, what's happening? Okay. If this is possible with universal approximation function, if we can always find these new states and channels, universal, I mean independent of the original state and channel, only depending on these sets, then we say approximate fixed point equations are fixable. So this is some definition. And now you see on this slide, I don't have much space for like another red box. So I'm a bit more hopeful that the answer is actually true here. And this is the case. So now we finally find a yes, okay, and we find this proposition. This is for a finite dimension Hilbert space, 2 sets, kind of like structures which are closed, S and C being closed. And we want them to have like at least one fixed point pair in them, because otherwise we will not be able to fix these approximate fixed point equations. And then in the kind of in the sense of the addition before, we always have fixability. And the result relies on a compactness argument. This is why we find existence of such approximation functions, but like in a rather implicit way, we don't get like explicit convergence rates. We don't really know how these F and G look like. We just know that they exist on this level. So now to connect this kind of rather abstract question about approximate fixed point equations to something people care maybe a bit more, I want to connect them to like my motivating example, which is the robustness theory of quantum Markov chains. Let me remind you what quantum Markov chains are. Those are, for the short cases, tripartite quantum states, rho ABC, which have conditionally mutual information, AC given B equal to 0. So by Pet's recovery, this is equivalent for a recovery channel to exist. So kind of operational, this means you can forget about system C, you can like trace it out, and then recover the full state and all of its correlation on ABC by just looking at the system B. Okay, this is quite nice. And then in the paper by Hayden, Jotzer, Petz, and Winter from 2004, relying on some kind of structural result about fixed point, the so-called Quashimoto theorem, they proved that you can kind of like have like explicit knowledge of how the correlations in the state look like. So they have this algebraic characterization, which tells you there's an orthogonal sum decomposition of the Hilbert space B, which is followed by the tripartite Hilbert space in this tripartite state in this way. And okay, this formula might look a bit complicated to you if you haven't seen it before, but kind of what this tells you is this is a natural generalization of the conditional independence we know from classical Markov chains, because this defines like a projective measurement on system B, okay? And you can do this and then condition on the outcome, let's say J. The post-measurement state here is a product state. So kind of you have independence of A and C condition on the outcome J, just as for classical Markov chain. So now I'm interested in robustness theory. So let's do approximate quantum Markov chains. We don't have conditional mutual information equal to 0, but rather small. And this is kind of like, especially in the quantum world, a very natural thing to study, because people expect and also know in certain cases that if you look at the Gibbs state of like a local Hamiltonian, for B being like a sufficiently large region separating A and C, the conditional mutual information is not exactly equal to 0, but decays in some sense in the size of this beam. So this is kind of like a relevant thing for condensed matter physics, and people have studied that a lot and tried to recover kind of like these characterizations. So in this breakthrough paper by Farzin and Renner, they have found that there exists a recovery channel. So we get still like approximate recovery, now with some scaling of the error parameter being square root of epsilon, importantly independent of the dimensions of the system. And kind of now, if you read this whole from left to right, here kind of quantum Markov chains, exact ones, are characterized by satisfying a fixed point equation for a specific kind of channel. Therefore, approximate quantum Markov chains are characterized by satisfying an approximate fixed point equation, again of a channel of the specific structure. Natural question to ask is, okay, whenever I have an approximate quantum Markov chain, does there exist an exact one close to it? And do we recover an approximate orthogonal sum decomposition, kind of like this thing here? And classically, the answer is very simple. So that's just because you can write the conditional mutual information of the tripartite probability distribution at as the minimal Kullback-Leibler distance of P to the set of classical Markov chains. And therefore, you recover all structural properties you're interested in approximately from this exact Markov chain. And if you're more interested in total variation distance, you just do Pinsker. But quantumly, kind of like upper bounding this minimal distance to the set of quantum Markov chains by some function which decays as the conditional mutual information goes to 0 is an open problem, in fact. And actually, there are many negative results which show you that any such upper bound must be dimension dependent. So we have like a couple of lower bounds, couple of counterexamples telling you that the whole problem is much more complicated in the quantum world compared to the classical world. So because I have this approximate fixed point equation, I can essentially apply the result on fixability, which I mentioned before, to the setup for kind of like general states and general states on this tripartite Hilbert space and channels of the specific form being this recovery form. And by that, I find like a first application, which is robustness of quantum Markov chains. So whenever I have an approximate quantum Markov chain rho ABC with small conditional mutual information, I find an exact quantum Markov chain sigma ABC close to it, where like this approximation function decays to 0 as epsilon goes to 0. However, as the result still relies on compactness, I don't have like explicit control on this function f. It's rather implicit. I just know its existence. To close this gap a bit, I want to study some concept which I call rapid fixability. And this essentially asks whether for like abstract approximate fixed point equations, I can find convergence rates, good control on these functions f and g. And what I would like to have is that they are of a specific form, like you see here. So kind of the way the dimension epsilon enter is a bit disentangled. So they just enter as factors. And the convergence as epsilon goes to 0 is rather fast. So like some kind of root here. And if this is possible, I say approximate fixed point equations for this pair S and C for these structures are rapidly fixable. Okay? And in the paper, we show that this is actually possible to do for many interesting structures. The most natural one is just kind of like general states and channels. And we have the following theorem. So whenever you have a state and a channel satisfying this approximate fixed point equation, you can find like a new state and a new channel root epsilon close to the original ones with an exact fixed point equation. What I want to highlight here is that we don't have any dimension dependence in the scaling. And furthermore, that the scaling is essentially tight. So there are families of states or like kind of counterexamples, rho and n, where we find like lower bound on like this maximum of like the possible approximation function. And there we see like the root epsilon scaling at least. We develop a few techniques to prove rapid fixability for many other structures. So this is kind of the result I mentioned, general states and channels. We can do classical states and channels like here. So this is like probability vectors and stochastic matrices. We still find like the root epsilon scaling. Then we could do something which might interest you, which are unitary channels. Now we find like a bit more complicated approximation function with like explicit dimension scaling. Mixed unitary channels, another even more complicated looking function, unital channels. And then we go to the bipartite setup where we have now only the pure states of some bipartite Hilbert space HAB. and C being the set of local channels, which act trivially on system A, and there we again find rapid fixability. On the other hand, this holds not true generically or like for all structures of interest. So one structure I was really interested in, which really much connects to the quantum Markov chains, is the following, which is again the bipartite setup, but now you have like general mixed states, and C again being the set of local quantum channels. In that case, we actually find impossibility of rapid fixability. So we find some kind of lower bound on the possible approximation function. And this is kind of like the last thing I wanted to talk about here and kind of flesh this out a bit how this works. In order to do this, I first need to extend the question of fixability to now doing multiple fixed point at once. So, okay, it's like just natural generalization. We just do two. Let's say I have two states, one channel, two approximate fixed point equations. And we can ask, do we find like a new two closed states and one new channel such that we have two exact fixed point equations? So like one channel which fixes both, okay? And here I also already demand that the scaling is like kind of in this preferred rapid way. And okay, this is some question you might ask and you might be hopeful, but no, this is not general and not possible in general. And this is even impossible in the classical case already. So there is like kind of a family of probability vectors P1 and P2 over kind of like dimension D and stochastic matrix T, such that we have like approximate fixed point equation with some error which decays exponentially in the dimension. But whenever you find two new probability vectors Q1 and Q2 in a new stochastic matrix such that you have two exact fixed point equations, at least one of the approximation must be really, really off. So you have like kind of a constant lower bound on either the stochastic matrix or one of the probability distributions. This is really kind of like a far gap between something which goes exponentially down and like a constant lower bound. And to connect this now back to the bipartite case for quantum states, what you can do, you can embed this counter example, putting them onto the diagonal of two quantum states. So you define like these rho P1, rho P2, then you put them into like two registers of a classical bipartite classical state, rho AB. And you can also define like a new local channel, NB, through the stochastic matrix T. By what I've shown you earlier, this local channel in this bipartite state satisfies an approximate fixed point equation, again with exponentially scaling error. But by the lower bounds, I mentioned you can kind of work out, what the lower bound for this odd-looking optimization problem. So you try to find like the best new bipartite state, the next best local channel, and then you try to find like the best distance in diamond norm to the original channel and trace distance to the original state. And this scales like in this logarithmic, at least in this logarithmic way in epsilon. Okay. And by that you see, okay, I cannot find new state and channel satisfying exact fixed point equation with error parameter scaling in this desirable rapid way. And this is just this impossibility statement. So as a corollary, we can summarize, we have impossibility to find rapid fixability for general bipartite states and local channels. And as the whole counterexample is actually classical, this already shuts it down for bipartite probability distributions and local stochastic matrices. So I want to kind of close with some open problems. So I've mentioned a couple of upper bounds on these approximation functions for like general mixed states and channels. And I showed you there that these functions are optimal, but in general, I don't know much whether they are optimal, especially kind of in the case of unitary channels. In unitary channels, I've seen that there's some dimension dependence. Whether this dimension dependence is necessary, I actually don't know. So it would be really cool to find like lower bounds and to prove that this dimension dependence is actually necessary. And then the relevant open problem, which connects back to the motivating example, is like improve the result on robustness of quantum Markov chains. Okay, so what we would like to have is an explicit upper bound on the distance from rho ABC to the set of quantum Markov chains, this which decays in a very nice, fast, desirable way as the conditional mutual information goes to 0. So this is kind of like the particular form I write here, which would be nice to have, is again inspired by like this rapid fixability business. So you have like a disentangled way how the dimension enter into the bound, and how the conditional mutual information enters into the bound. And obviously what you really would like to determine are all of these constants, BA, BB, BC. For example, what is not shut down by the counter examples and would be nice to have for kind of like again, thinking about Gibbs states, taking thermodynamic limits, is that you might not have like any dependence on a dimension dB here. So this BB here is equal to 0, but we don't have any kind of bound like that. We also don't know whether such thing can hold true. So this is kind of like a big open problem. And I would like to thank you a lot for your attention.
Thanks for the great talk, Robert. And we have plenty of time for the questions. So, any questions?
Sorry if you mentioned it in the talk and I missed it, but how critical is the rapid fixability property for what you have in mind? I mean, okay, if you want to get specifically this kind of dimension scaling, then I guess so, but like, is there a specific reason why you want like power scaling in the dimension and the epsilon?
I think I just like kind of the form of it, and I thought kind of often you have like you know how epsilon kind of like this thing scales in the dimension of B, so you kind of want to shut down scaling you have here by the scaling here. So kind of like I think they should enter in some sense on the same footing.
I see.
But okay, I think like the way I came up with the rapid fixability form is that I try to prove like upper bounds for several structures, and they always look like that form. And okay, then I generalize this, try to actually prove like something similar for the robust, for the quantum Markov chains. And the thing there is like the structure of interest is actually the one where I have like an impossibility statement. So if you could prove nice upper bound for this structure here, you could kind of plug it into the construction of where you of this orthogonal sum decomposition to find like good bounds on the distance to quantum Markov chain. And therefore it's kind of like said that we have the counterexample here because this doesn't lead much.
I see. Thank you.
Thanks.
More questions?
Hi, thanks for the very nice talk. So I just have a naive question regarding the very first part of the talk. So you have two no-go theorems for fixability of just a state and the fixability of the quantum channel, but that's generic, right? But if I promise, for example, the channel case that it has some structure, do we have sufficiently large class of channels that you can fix in that way? Counterexamples really kind of like a random in.
I mean, I think like the counterexamples are just the kind of like things I came up with. I think like once you like for the first question, I think most things will fail. So if you try to find like a new state, where is it? This. No. If you just try to find like a new state, I think you can for most channels of interest cut down. Like whenever you have like uniqueness of fixed point space or like kind of where you control the fixed point space of this map N fairly well, you know kind of like how this fails. And the other example here, the counterexample is like a unitary channel. So it's already kind of like a nice structure where the counterexample hold. But no, I don't know whether kind of like you might be able to fix the fixed point equation by just changing one if you have like a specific other structure.
Thank you. I do have a question. Yes. Regarding your open problem, do we know any of interesting upper bounds that are not related, that they involve other quantities and not the multi-information? So like your upper bound, your upper question about do we know of interesting upper bounds that do involve other quantities, like not the multi-information?
Okay. No. So kind of, I mean, okay, it depends on what you like to have. I mean, you can write down something almost trivial, but like kind of when you want to start with something entropic here, which implies approximate recoverability or so, you won't get this. So like my starting point, okay, I write it here in terms of the conditional mutual information because this is maybe like something which is a bit more known. It's also nice to have like here something purely algebraic and here something entropic. Yeah. But my starting point, as you might guess from like the whole fixability business, is actually I have approximate recoverability, and then I try to find like a closed quantum Markov chain, and everything kind of which goes in that direction is completely open.
I see. Okay. Do you have time? be shy.
Sorry, this one I think is just a lack of background in the field, but so I was just like vaguely aware of the fact that low CQMI is not quite the same thing as close to a quantum Markov chain. But so you're saying that the only sense in which there's counterexamples is that there's a dimension dependency in this.
We have kind of explicit lower bounds in the sense of we have families of states running through the dimension where you know, okay, the conditional mutual decays as like 1/d essentially or so, but you're constant away over the whole family from the set of Markov chain. You kind of know a bit the scaling, and therefore there must be a dimension dependence, yeah.
Yeah. But in the sense that the structure of these counterexamples is such that in some sense, if you want to get, so to speak, like arbitrarily bad violations of this property, then you must also go to arbitrarily high dimension.
Sorry, could you?
Sorry, as in the classical version would be that if you have low CQMI, then you're close to a Markov chain.
Yeah.
Quantum, this does not exactly, this property doesn't carry over. But if you want to get a arbitrarily bad violation of this property in the quantum case, you would also have to go to arbitrarily high dimension.
You know, also kind of like results in a kind of fixed dimension where you know that the scaling, you would like a kind of like in the classical case, you see like linear scaling, or I think it's square root scaling or so, and you know that it's kind of like the scaling, how the error parameter enters is kind of worse. There's a dimension lower bound, but also kind of like how the root power essentially is.
I see.
Yeah.
Okay, thank you.
Thank you too.
Do we know if the dimension dependence is polynomial? Could it be like super polynomial?
Also no. Like lower bounds are all, I think, worst one I know is like log, kind of you have a decaying, or it's like D over log D, I think. That's the worst we know. Okay. And this is kind of in the A system and the C system. But okay, it could be like way worse, so this is all open.
Okay. Final questions? Or if not, let's thank Robert again.
Thank you.
This one, right? Oops. Just plug. I would suggest plug on your right side because I guess you'll be looking on the other side because you're gonna be looking this way.
This one.
Yeah.
Okay.
Now it's off, and when you want. Yeah, it's not. I can't make it work, to be honest.
So I still need to.
Yeah.
Push.
Yeah.
Okay. Just use.
Only the laser was. I don't know why. Okay, everybody, let's everyone take their seat. So it's my pleasure to welcome the third and final speaker of this session, Mo Yin, who's going to talk about reversing quantum process. Please, the stage is yours.
Thank you. So, hello everyone. Welcome to the last talk today. I'm Mo Yin from the Hong Kong University of Science and Technology, now in Guangzhou. Today I'm going to talk about one of our recent work, reversing unknown quantum channel based on the technique called virtual comp. So to help you understand better the setting of this problem, we can further think about this scenario. Suppose you have some quantum state rho, which just pass through some unknown quantum process, as shown by the black box here. So now it becomes some unwanted state sigma. So for this unknown process, you can think, for example, it can be a magnetic field in some space, so your state just suddenly pass through it. Or it can be some unknown noise in your quantum hardware. Or it can be a quantum device given by one of your colleagues from some experiment group, but he just forgot to tell you what it is. So to you, this process is a black box, but in these examples, you can see you can still query it and use it again for many times. So now the question is, if you don't know what is this process and you don't want to do process tomography to know what it is it still possible to get back exactly the original state rho? So now what you can do is just by querying this black box, use it again for many times, and also perform some other operations. So if possible, then this whole part performs like the inverse of this quantum channel. So I think for people who first see this problem may think it is quite amazing, because how could you just perform this operation again and again for many times? Then it suddenly becomes the inverse of this process. But actually, it is possible. And when this unknown black box is a unitary gate, then there have already been many interesting studies. And there are two very exciting results recently. One is last year, the first protocol for qubit unitary gate has been derived, which shows that you don't need to use you don't need to know what is this unitary gate, but by just querying it for 4 times, you can reverse arbitrary qubit unitary gate. And a more exciting result this year is that people show that for arbitrary unitary and arbitrary dimension, there exists a general quantum protocol which can reverse all these unitary gates deterministically and exactly by just querying it for finite times. So this reverse is actually possible. So now come back to our problem. If this black box is not just a unitary gate, but a general quantum channel, is this still possible? And I think one thing you will first notice is that the inverse of a quantum channel is usually not a CPTP map. So it is not actually a physical process. So to deal with this, today I will first talk about these two concepts, about two related works. The first is about virtual process, which is used to reverse a given quantum channel. And the second is about quantum comp, which is used to reverse unknown unitary gate. And after introducing this, we will combine these ideas and have this virtual comp. And then we will use this to solve this problem to reverse the unknown channel. And then I will show some theoretical results and applications. So first, about reversing a quantum channel, we know that in general, usually the inverse of a CPTP map is actually an HPTP map. And this can be done because for arbitrary HPTP map, it can be defined in decomposed in an affine combination of many quantum channels with positive and negative coefficients. So based on this, all HPTP maps can be simulated while sampling and post-processing. And this technique has already been used in error mitigation. we know that in probabilistic error cancellation, for example, there is a depressing noise in your quantum circuit. And in this case, we know what this noise level P is. And then what we can, if we want to cancel this error, what we can do is just first calculate the inverse of it and decompose it into different quantum channels. For example, the inverse of the depressing channel is equal to some coefficient alpha times the identity channel minus beta times the Fourier depressing channel. So then what we can do is perform the identity channel after this depressing noise, or you perform a Fourier depressing channel after it with this probability distribution related to these coefficients. And in average, the outcome of the first one minus the outcome of the second one will be proportional to state rho. So it realizes the inverse of this depressing noise and cancel this error. So this is based on virtual process to realize a given channel inverse. And the second thing I need to introduce is about quantum comp. So in quantum computing, we not only can do transformation on quantum state, transform it to another state sigma, we can also do transformation on quantum operations, transform an operation E to an operation F. And in general, this can be done by this quantum network called quantum comp. And in this figure, it is a one slot of quantum comp, which means it just uses this operation for one time. And you can see that after you input this operation you want to transform, then the whole process becomes an operation from Hilbert space C to Hilbert space D, which is related to the target, the operation you wanted. And in general, to transform an operation, you can use this operation for many times. And in general, what we can use is an n-slot quantum comp. So it is a quantum network where you can insert this process for n times here. And here, Julio and others have shown that arbitrary n-slot quantum comp have this Choi, can be represented by the Choi operator in this mathematical formula. And I don't want to go to the detail for this, but we just need to know that to find a feasible quantum comp, we can do this by finding the Choi operator with these conditions. So now, to reverse an unknown unitary gate based on quantum comp can be formulated like this. So now our problem is for arbitrary unitary gate, we need to find an n-slot quantum comp, which will take n copies of this unitary gate as input in each slot. And then the whole process from P to F now performs like the inverse of this unitary gate for arbitrary unitary. And previous results have shown that such quantum comp do exist, which can perfectly reverse all these unitary gates. So based on these two ideas, we have this virtual comp. So it is just an alpha combination of many quantum comps with positive and negative coefficients. So to realize a virtual comp, we just need to, we also just need the sampling and post-processing of these quantum comps. And now for our problem, to reversing an unknown channel, it can be formulated like this. So here, unknown channel means this channel is from a given set, from N1 to Nm, while the elements number can be finite or infinite. So here we just know that this channel is from this set, but we don't know what exactly it is. And now the problem is to find a virtual comp here, which will use this unknown channel for n times. And then the whole process performs like the inverse of this channel for all these channels in this set. So it will give us the original state rho at last. So for this problem, to reverse all these channels in this set based on virtual comp, now let's see some theoretical results. So the first situation we consider is about still about reversing depressing noise, but here what is the noise level is unknown. We only know that it is from a given set with elements P1, P2 to Pn. While for the continuous region, noise level in continuous region, which have infinite numbers, we'll discuss about it later. So now let's see this situation where this set have finite elements. Then the first result we found is that if there are two possible candidates, P1 and P2, then we can always find a one-slot virtual comp that can reverse both these two depressing noise by just querying it for one time. So we don't need to know whether which process is, whether it is P1 depressing with P1 or with P2. This virtual comp can always perform the inverse of it. But if there are three elements, then one slot virtual comp is not enough to perform perfect reversion for all these noise. So if one slot virtual comp can reverse P1 and P2 perfectly, then for P3 there will always be some error. So to reverse this set, then we need a two-slot virtual comp, which means querying this unknown process twice. So in general, here comes our first result. For a depolarizing noise with the noise parameter have n+1 candidate, so it can be either P1, P2, or Pn+1. Then there always exists an n-slot virtual comp, which will use this unknown process for n times, and then realize the inverse of it for all these noise levels. So this is our first result. So here, let's make things more clear. So here, what we know is that this depolarizing is from this noise set with n+1 candidate. And what we don't know is which one exactly it is. Then we can always find this n-slot virtual comp that use this depolarizing noise for n times. And then the whole process will perform just like the inverse of this unknown process. And there are some other points I need to point out. First, if you want to use a quantum comp, or even a probabilistic quantum comp, so you will not allow some failure, then it doesn't work. So virtual here is necessary. And the second thing is we found that for n slot, n+1 candidate is already the optimal number. So if there are n+2 candidates, then no such n-slot virtual comp exists, can perfectly reverse all these depolarizing noise. And this gives us this no-go theory. A virtual comp with finite slot cannot universally reverse all quantum channels. This is something different from unitary case, as previous results have shown that there exists a finite slot quantum comp can universally reverse all unitary gates, where here a finite slot virtual comp cannot universally reverse all quantum channels. This is something different from channel and unitary. So besides the depolarizing noise, we also consider the situation about the general quantum channels. So here, this result, we have a theoretical proof for this result that by using a one-slot virtual comp, we can always reverse any two quantum channels. So which means if you are given two quantum channels, no matter what it is and no matter what the dimension it is, but they are all invertible, then we can always find a one-slot virtual comp that can reverse all these quantum channels by just querying it for one time. And we have theoretical proof in our article. And besides this, we also have an observation based on numerical results, which shows that if we randomly generate a qubit-to-qubit quantum channel, and we generate 13 different qubit channels, then we can always numerically find a one-slot virtual comp which can perfectly reverse all these elements. But when we generate 14 different quantum channels, then no such one-slot virtual comp exists. And intuition here is that qubit-to-qubit quantum channel can always be determined by 12 different parameters. So 12 plus 1 is equal to 13. And while the proof here is quite difficult, so actually we don't know how to prove it yet. Okay, the last theoretical result is about reversing depolarizing noise in a continuous region. So before we have shown that with a finite slot virtual comp, we cannot reverse all these depolarizing noise perfectly because there are infinite many elements here. So what we can do is to reverse it approximately. so that for all this noise, after this whole process, it will be close to the identity quantum channel. So here, the distance is measured by the diamond on here. And we found that by just using the previous protocol, which is an n-slot quantum comp, which can perfectly reverse P1, P2, and the n-1 elements in this range, in this region. This protocol already works quite nice for all these noise levels, and we have proved that the worst case error for all these depressing noise will decay in the scale 1/n. So here is a numerical experiment we did by using 1, 2, 3, 4, 5. So pairing this unknown depressing noise for 1, 2, 3, 4, 5 this time for this noise region. And we can show that the worst case error decay very fast. And when we query it for 5 times, they already, for most of these depressing noise, they are already very close to the identical quantum channels. So now let's see some applications. The first application is a direct application of the previous result. So here we can use it in error cancellation. So before we show that in probabilistic error cancellation, it deals with a given quantum depressing noise. So we need to know what this noise level P is. Well, here, using this virtual comp, we can cancel this depressing noise in our region, and we don't need to know what exactly it is. And to physically realize it, to remember that virtual comp can be decomposed in an alpha combination of many quantum comps. So we just need to find some quantum comps that is simple to be, it can be implemented easily in our laboratory. And here we found a quite simple decomposition, where what we need to do is either you do nothing on the received state, so perform the identity operator, or you perform the fully depressing channel on after this unknown noise, just as what we did here in the probabilistic error cancellation. Well, the difference is we also need to perform this. So we need to query this depressing noise again for k times, where k is from 1 to n. So here we just need to sequentially perform this unknown depressing for k times on the received state. So we just let our state go through this unknown process again and again for k times. And the probability it can be calculated based on by solving those problems. So here what we show is that this is actually physically can be realized, and it has this realization so that maybe in some experiment, we don't need to first do tomography to know what is this depressing noise. And then we can still cancel it by using this virtual comp technique. And for most of these errors, it will decay very fast. It will goes to the identity channel in the scale 1 over, the error is in the scale 1 over n. So the second application is using this to realize unity inverse. As before, we have shown that quantum comp has already shown that with a finite slot, quantum comp it can reverse arbitrary unity gate. And here, an interesting result here is that using virtual comp, arbitrary unity gate, no matter what the dimension is, we can always use our one-slot virtual comp to reverse this unity gate. So actually the circuit here by using virtual comp will be much simpler than using quantum comp. And we also calculated the sampling overhead for using virtual comp, which have a relation with the fidelity of using quantum comp. And here the cost of estimation, the sampling overhead shot related to the cost for estimating this value. So I don't go to the detail here. I just want to mention one numerical result we found. If we want to estimate this value, which means we have some initial state at 0 bar 0, And by using just using unity gate U, we want to estimate U dagger K0 bar 0 U, the expectation value of it on the observation Z. Then this numerical result shows that on the same number, query number for this unknown unity gate, the one slot virtual comp have a better performance than the optimal 4-slot quantum comp. So you can see the simulation error is lower, and also the variance is smaller. And the last thing I want to mention is just if you combine the previous two applications, then you can also have this protocol, which is now the unknown process is a unit gate after deploying noise. While here you both don't know what is this unit gate U, and you don't know what this noise level is. Well, here you can still construct this virtual comp which just querying this U and deploying noise after deploying noise dp for finite times, and then you can get back perfectly this original unit gate U. Well, in the whole process, you don't need to know what is this deploying noise, and you don't need to know what is this unit gate U. So here it shows that it really could be done by using this virtual comp. So that's all for today's talk. And if you just need to remember one sentence in this talk, it will be, if you want to reverse an unknown quantum channel deterministically and exactly, then it is possible by using this virtual comp. And here we have shown some results in reversing deploying noise, general quantum channels, and also approximate reverse deployed noise. And we see applications in error cancellation and also unitary inversion. And thanks, that's all.
Thanks for the nice talk. Do we have questions in the audience? Okay, one there, two there.
Hi, thanks a lot for a very interesting talk. I have two questions. So one is that how fundamentally is your method different from like the method by Yoshida et al., where I think, to my best understanding, is relying on the symmetry of the totally anti-symmetric state to revert the unitary. I don't know if it's wrong, Yoshida can correct me here, but how is this fundamentally different in your case now that you're using like having channels instead?
I think the difference. So here, both in our virtual comp and in their result for reversing these things, we use this quantum structure. So in this sense, we both use semi-definite programming to see whether it is there are feasible solutions or not. So in this sense, they are the same. What difference is that this virtual comp, so to realize, so quantum comp cannot be used to realize this channel inversion. So previously, like what they did is usually in those unitary inversion, which can be done by quantum comp. Well, here, if you want to reverse unknown quantum channels, then you really need to use virtual comp. As in our article, we prove that if you quantum comp probabilistically, then there are some constraints that forbid you to reverse quantum channels. So that here we need is the virtual comp. And mathematically, maybe if you want to know the mathematical difference, then it is just the constraint for virtual comp and quantum comp are different in those semi-definite programming problems.
Okay, thanks. And the second question is, like your virtual comps has negative coefficients. So how do you see how you can easily implement it in actual applications?
The negative coefficients for this is just quite nature as people previously did for probabilistic error cancellation. So as I mentioned, so here this is a decomposition for an HPTP map. Here has the negative coefficient here. So here is a simulation of it by just probabilistically perform the identity channel and probabilistically perform the deploying channel. And in average, so here the average is you get the output here and minus the get output here, and they will in average be equal to this to the target to this HPTP map. So this is usually used in calculating this calculating these things. So in estimating some state after some observable, so you can statistically calculate this by the +1 minus -1.
Okay, thanks.
He asked for. Oh, yeah. Give it.
Hi, thanks for the nice talk. On one of the slides, when he showed how to reverse depolarizing noise, there was this parameter K for the number of times you repeated.
So you mean this one or
depolarizing? I think it was in the applications section. Yeah, you apply the process to the receive state K times. How do you?
You mean this one?
Yeah, how do you choose K? And does it like, do you know the impact on the success?
So here this is and so here let's consider the realization for an n-slot virtual COM in this protocol. So this n-slot, which means you will use this unknown depolarizing noise for n times. So how to so this virtual COM can be decomposed into n+2 elements. So while the first element is identity channel, which just quantum COM that don't use this depolarizing noise. So you just pass through it away. And this is a quantum COM that just goes through a fully depolarizing noise and don't use each one of it. And CK is, and then the other n terms are those which will access this unknown depolarizing noise for 1 time, for 2 times, or for 3 times. So there are different. So there are these n+2 different quantum COMs, which actually for sure finally looks just like this, and they can be. And so here is just an example for sequentially perform this for 3 times.
Okay, yeah, thank you. And then how does the sampling probability compare to that of doing probabilistic error cancellation? The sampling cost even, sorry.
So the sampling cost actually depends on both 2 things. So one is the n here. So how many noise you want to exactly reverse, and one is the noise region P1 and P2. If for P1 to P2, if I remember clear, they are small, then the sampling overhead is also small. If they are large, then I think there is a table in our appendix. If not, you can send me an email. So it depends on these 2 things.
Okay, thank you.
One question down there.
I wonder if you have thought about COMs with more than 2 inputs and 2 outputs. Like in other words, reversing 2 qubit gates or channels with multiple inputs and multiple outputs.
Sorry, I'm not very sure about this.
If you consider a single COM, there's multiple COMs concatenated, and each single COM consists of 2 inputs and 2 outputs, right?
You mean 2 input and 2 output? Or?
Just consider 1 COM, and you are plugging in a 1 qubit gate, right? So the COM has 2 inputs and 2 outputs. So what if the gate is 2 qubit gate?
Because here we have a 2 qubit gate can be regarded as a system with dimension 4, right? So there, for this result, if we just need to change the dimension for the input channel you considered. For example, in this result, it doesn't depend on the dimension of this channel. So for arbitrary two quantum channels, there is this.
It's not about dimension, it's about the independent inputs. If the channel has independent inputs and independent outputs.
So you mean a channel? So for example, here N1, you mean the input and output have different dimensions?
Maybe different dimensions, but different inputs and different outputs.
Okay, maybe I don't really get that point, or maybe we can discuss later.
Sure.
Okay, let's thank Moin and all the previous speakers in the session. This concludes the day. Have a nice lunch and afternoon, and see you for the banquet. Very good.